Hello friends, today we are going to see hydrostatic forces on inclined plane surface immersed in liquid. Consider an inclined plane surface of arbitrary shape. Let us name this plane surface as R and S. Let G be the center of gravity of this arbitrary shape which is inclined to free surface of liquid and making an angle theta here. The distance of Cg from the free surface of liquid is h bar and Pb the center of pressure whose distance from free liquid surface is s star. Consider an axis OO, you can see here OO. Let y bar be the distance of center of gravity from axis OO and y star be the distance of center of pressure from OO. We will directly start with the derivation as the basic concept like total pressure and center of pressure we have seen in previous lectures, and those who have not seen the previous lecture, I have provided the link of previous lecture in the description box. I'll request you to please watch the previous video for clearing your basic concepts. So let us begin directly with the derivation. First we'll calculate total pressure. From hydrostatic law we know the pressure is given as rho gh, right? So we'll consider a small elemental strip of thickness dy and area dA. So total pressure force acting on this elemental area is given as dF. Pressure force is pressure intensity into area, so pressure intensity is rho gh into area is dA, but we are not interested to find out the total pressure acting on this elemental area. Our aim is to find out the total pressure acting on the whole arbitrary area. So to get total pressure on entire area we will integrate dF. So total pressure on entire area is given as F, which is equal to integration of dF over this entire area, which is equal to integration of rho gh dA. As rho and g is constant, we will keep rho and g out of integration and will integrate h and dA. So h is nothing but the distance of dF acting on small elemental area. So this distance is nothing but h, and dA is the area of this elemental strip. So after integration rho g as it is, h becomes h bar, that is distance of Cg from the free surface of liquid, and dA over the entire area will become A. So finally we get F is equal to rho g A h bar. We'll make this as equation 1. As we can see from the figure, the inclined plane surface is making an angle theta with the free surface of the liquid. If we draw a triangle like this, let us say this is 90-degree angle and this is our theta. So we can write for sine theta is equal to h by y, or h by y bar, or h star by y star. So we'll keep this for our reference. From the figure we can write for equation 1, F is equal to rho g a, and instead of writing h bar, I'll write it as y bar sine theta. Let us go for second part of derivation, that is center of pressure. It is based on principle of moments, just like we discussed in previous session. So first we'll find out pressure on any elemental strip. Pressure on elemental strip is given as dF is equal to rho g h dA. But again, looking at this figure, for h we can substitute as y sine theta. So dF becomes dF becomes rho g dA y sine theta. Now moment of dF about axis OO is given as dF into y. We know that dF from this equation is rho g dA y sine theta into this y. So equation becomes rho g dA y square sine theta. Now sum of moment of small forces about OO is given by integration of dF. Now sum of moment of such small forces about OO is given by integration of dF, which is equal to rho g sine theta out of integration, as these are constant, integration of y square dA. As discussed in previous session, y square dA is nothing but second moment of area, that means moment of inertia, and which is given by I0. So you can write this equation as rho g sine theta I0. Let us make this equation as equation A. Now moment of resultant about OO is given as F into y star. Let us make this as equation B. Equating equation A and B, we get F into y star is equal to rho g sine theta I0. But we know that F is equal to rho g AH bar. So substituting in this equation, so equation becomes rho g AH bar into y star is equal to rho g sine theta I0, cancelling out rho g from both the sides. We also know y star is equal to h star upon sine theta. From this particular equation, y star is h star upon sine theta. Substituting y star in this equation, We get h bar into h star upon sin theta is equal to sin theta I0. Further simplifying this equation, we get, substituting y star in this equation, we get a h bar into h star upon sin theta is equal to sin theta I0. Further simplifying this equation, we get h star is equal to sin square theta I0 upon a h bar. We know from parallel axis theorem, I0 is equal to Ig plus a y bar square. Substituting this equation, we get a star is equal to sin square theta Ig plus a y bar square upon a h bar. But we know that y bar is given as h bar upon sin theta. So substituting in this equation, we get h star is equal to sin square theta Ig plus a as it is. Instead of writing y bar, we substitute h bar upon sin theta the whole square. Now opening the bracket, we get sin square theta into Ig upon ah bar plus ah bar square upon ah bar, as sin square theta and this sin square theta get cancelled. So we get our final expression for center of pressure, that is h star is equal to Ig sin square theta upon ah bar plus h bar, which is the required expression for location of center of pressure of an inclined plane surface immersed in liquid.